Hello, hello. What do you say? Okay. So Hi, I'm audible, right? Oh, maybe you can wait for 2-3 minutes and then we can start. Oh, is it class is still going on? Huh? Okay, you can wait for some more time. So today's will be the most likely be the final class of this session. So like next, I think January 31st is the last day for the final class. I think so. Next Wednesday will be February 1. So I think this is most likely our final session for this time. And gate is on 5th, right? Sunday, no? EC gate. So mostly we'll be having only class this session. Next Monday and Tuesday classes are there, but next Wednesday's class I don't think it's there. I'm not very sure. Shall we wait for 2 more minutes? Okay, then maybe we can start. So other class is over, right? Still going on. Okay. I don't know. Maybe we can start and yeah, I think we can start. I'm still audible, right? Okay, thanks. So, hi, good evening. My name is Prasav. I'm doing my PhD in IISc Bangalore. So, every Wednesday during this time, we'll be meeting to discuss gate problems on signals and systems, max, and some topics in communication, etc. So, today we'll be again discussing few miscellaneous topics in signals and systems. And by the way, this is most likely be the final session of this time. So maybe we can start by discussing this question. So if at any point if something is not clear, like please let me know. I think that class is still on, so maybe we can get started. About three of us are there, I think. Four, I think. Okay, let's start. So we will begin by discussing this question. This question appeared in GATE 2019 EC paper. So this is actually a simple question. So the question is like this. Let me turn off my video. I think it is a bit slow. Okay. So consider differential function f of x on set of real numbers such that f of minus 1 is 0 and mod of f prime x is less than or equal to for all x. Given this condition, which one of the following inequalities is necessarily true for all x in minus 2, 2? So basically we are given with a function f of x which is differentiable everywhere in the real line, and the value of f at minus 1 is 0, and also the derivative is always bounded by 2. The modulus of the derivative is always less than or equal to 2. So given these facts, we need to choose the correct option that describes an inequality which is true for all x in this range minus to 2. So to solve this question, we can use what is known as mean value theorem. So the theorem goes like this: let fx be a function continuous in closed interval ab and differentiable in open interval ab. Then there exists a point C in open AB such that derivative of the function at that point is exactly equal to f of b minus f of a by b minus a. So this is the mean value theorem. So what it says is, suppose f of x is a function that is continuous in closed interval AB and differentiable in open interval AB. Then there exists a point C in this open AB such that the derivative of the function at that point is f of b minus f of a by b minus a. That is given. So now to answer this question, we are interested in the range minus 2, 2. And given that f of minus 1 is 0. So to solve, let us see, consider x in the interval minus 1 to 2. Suppose we have a function like this. Consider this interval. Then what happens? We have x in minus 1, 2. Then, and of course, this function, it is given that it is differentiable everywhere. That means it is also continuous everywhere, and it satisfies all the conditions that are necessary for us to apply the mean value theorem. So consider x in this range. Then what it means? Then there exists a c in this interval such that sorry. Let us consider the interval minus 1 to x. Consider where this x is between minus 1 and 2. Now what it means? There exists a c in this minus 1x such that f prime of c, the derivative of c is f of b. B is x here minus f of a by b minus a. This is clear, right? I just applied the mean value theorem with a equal to minus 1 and b equal to x. That's it. Up to here it's okay, no? Now what it's given, also given that modulus of the derivative, this is always less than equal to 2, which means that mod of f prime c is also less than equal to 2. Correct, no? Because it's the derivative is bounded for any x. That means even for this derivative that has to be true. So what it means? Mod of f of x minus f of minus 1 by x plus 1 is an equal to 2. And since we know that f of minus 1 is 0, we have mod f of x less than 2 times mod x plus 1. So up to here is okay, right? Any doubt? It's okay, right? So right now we have considered the interval from minus 1 to x. Now the question is for x in interval minus 2 to 2. But that is easy. We can do the same thing for the other case also. Suppose x is now in minus 2 to minus 1. Then consider the interval x to minus 1. Then again the same thing you can do. We can apply the mean value theorem. F prime c will be, then there exists a c in x minus 1 such that f prime c is f of b is f of minus 1 minus f of a by b minus a. This thing. Again I apply the same thing but in a different way. That's it. So this means what? Minus f of x by minus 1 plus x. Now the other result that we have, mod f prime c less than equal to 2. This implies that mod of minus fx by minus 1 plus x less than equal to 2. Or again we get the same answer. Mod of x less than equal to 2 mod x plus 1. So either way, we just did the second part for the sake of completeness, but by here we already know the required relation. So what it means is that the correct answer is option B. So for I think some for the people just join now, I'll just go through the solution once. So we given with a function, and it is given that f of minus 1 is 0 and f prime x, that mode of that is less than equal to 2. Given this condition, which of the following inequalities is necessarily true for minus 2, 2? So to solve this question, we used what is known as mean value theorem, which says that if fx is a continuous function in closed AB and differential in open AB, then there is a point C in this open AB such that f prime C is f of b minus f of a by b minus a. Then we just applied the mean value theorem in the interval minus 1x to get the result that f of x minus f of minus 1 by x minus minus 1 is this f prime c, and that will lead us to the result mod f x less than equal to 2 times mod x plus 1. Similarly, we choose the other interval and apply the same mean value theorem, we ended up the same result. So the correct is mod x less than equal to 2 mod x plus 1. So if I have more time at the end, I can explain this at the end, but yeah, for the time being, I think so. Option B is the correct answer. So, is there any doubt? Shall I proceed to the next question?
Yes, sir.
Okay, thanks. So, I think this one is a question on residues. I think Hari asked this question. He is not here now. Maybe we can come back to it later. I will do other question now. Yeah, this one I can do. This is again on complex analysis. So, the question is like this. So far it's okay, right? I can proceed now.
Yes, sir.
Okay, thanks. So the question is like this: a simple closed path C in the compass plane is shown in the figure. So there is a curve already. So usually you will be given with circles or things like that. But here it's a different curve. I mean, I don't know what, I think it's called a cardioid, but doesn't matter. We have a curve here. This is our curve gamma. Now, sorry, it is given this simple closed path C in the complex plane with anti-clockwise orientation, that is positive. We have now, suppose that this integration over C 2 raised to z by z square minus 1 dz is minus I pi times a. If that is the case, then what is the value of a? That's a question. So usually you will be given with a curve and we will be asked to compute the integral over that curve. But in this case, integral is given and the curve is also given, but we need to find what is the unknown value here a. So to answer this question, let us again review what is known as Cauchy's integral formula, or it is also part of the Cauchy's residue theorem. Residue theorem I will cover after like some 15 minutes. I'll see if Hari joins, otherwise I'll anyway cover after that. So what do we have? Integration over C. Theorem is like this. Suppose I have a simple closed path C with positive orientation, and yeah, I have f of z is analytic function. So this is analytic inside and on this curve that we have. Then this integration is given by 2 pi j times f of a. This is the Cauchy's integral formula. Sorry. So this I think we have already discussed in last week. So is there any doubt? Can I continue? Can I continue, right?
Yes, sir.
Okay, thanks. So what do we have here? In this case, the function is like this. We have integration over c 2 raised to z by z square minus 1 dz. Now, if you see this curve here, denominator z square minus 1 will be 0 for z equal to 1 and minus 1. That means there are two poles, one here and one here. And again, as usual, only one of them is inside the shape. So we only need to worry about this pole. So I can write the function like this. This integration I can write integration 2 raised to z by z minus 1 into z plus 1 dz, or I can write it like integration 2 raised to z by z minus 1 whole by z plus 1 dz. Now if you see the numerator here, 2 raised to z by z minus 1, this function is analytic. This is why analytic? Because it's a ratio of a exponential function and a linear function. Both of them are analytic, so here it's analytic. This is by the way, analytic means complex differentiable. So I'm going a bit fast because same thing we discussed last week also. So if something is not clear, please let me know. So this is analytic in the considered region. We only need to worry about this inside pole minus 1 0. Now this by Cauchy's integral formula, this is 2 pi j times 2 raised to z by z minus 1 at z equal to minus 1. This part is clear, right? So I just apply the Cauchy's integral formula, which says f of z by t. Yes, please.
So that z minus 1 is included with f of z. No, why z plus 1 is not included? How to choose?
Okay, so yeah,
how to choose between
so
the two?
yeah. So what happens here is if we see this thing, the function is 2 raised to z by z minus 1 into z plus 1, right? And we want to integrate this function here, correct? No. Now, what Cauchy's integral formula says is that suppose, sorry, okay, right?
Yes, sir. Continue.
Okay, okay, yeah. So what we have is from the Cauchy's integral formula. Suppose I have an integration like this, where the numerator is analytic and denominator is of the form z minus a, z minus a or z plus a, it doesn't matter. But the numerator should be analytic. Now, if I have in this kind of form, then the integral is nothing but 2 pi j times f of a, where f is whatever we have here on the numerator. Now, if you see this function 2 raised to z by z minus z plus 1, I can write in many different ways. But I want it to write in such a way that I have a z minus something on the denominator and something analytic on the top. Now that leaves us with two options. Either I can write 2 raised to z by z minus 1 by z plus 1, or I can write 2 raised to z by z plus 1 by z minus 1. Correct, no? These are the two ways in which I can write.
Yes, sir.
Okay, right? Okay. So now, if you see this case here, the pole that is problematic is inside here. So what I'm telling is that if we consider this function, like let's say this function, 2 raised to z by z plus 1, this function is infinity at z equal to minus 1. Or basically for a point inside this curve, this thing is infinity or this is not analytic. So this basically, if we have 1 by 0 kind of thing, we say that it's not differentiable for real functions, right? So similarly for complex functions also, whenever we have things evaluating to infinity, at that point the function will not be analytic. So if I split like this, the assumption that the numerator is analytic is not correct. Whereas if I split like this, then this numerator is, is a finite number and it is analytic in the region that we are interested in. That is the reason why we are splitting it like this. Is that okay?
Yes, sir.
Okay. So where were we? Okay, yeah. We need to validate this thing. So this is like 2 pi j 2 raised to minus 1 by minus 1 minus 1. This is like minus 2 pi j 2 inverse by 2. And okay, that's fine. That is like minus pi j by 2. This is the thing. Now what is given in the question? It is given that the answer is of the form minus I pi. Okay, I use j for I sometimes. So I equal to root of minus 1. I also say j is minus 1. Same thing, doesn't matter. What I have even. So now comparing these two, minus j pi a pi by 2 or a is half 0.5. So the value of a is 0.5. Is that okay?
Yes, sir.
No. So any other doubts? Shall I continue?
Yes, sir.
Okay, thanks. Maybe I'll explain that residue theorem now. That's kind of useful. Let's see. So I'll not be going to too much details. So okay, before that, why do we need to study this? So consider this kind of an integration, or even to be simple. Here in this case, we had only one pole inside the considered region. What if there are more poles? What if there is a pole here? What is there a pole here? Like that. So in that case, we will not be able to split it like this. Whatever way we split, there will be at least one term that will be going infinity in that considered region, right? So whatever this Cauchy's integral formula, that will apply only if we have a single pole inside the given region. If you have more than one pole, it won't work. So to evaluate such integrals where we have more than one pole, or to be more general, more than one singularity in a given region, we can use what is known as Cauchy's residue theorem. Now there is a bit of theory there. I don't want to go into too much details here. I'll explain the simple way here. And again, like a word of caution, this is not a substitute for a proper course on complex analysis. I'm just telling it from a point of view that you can use it for gate exam. The theory is a bit more involved. So residues, to define residues, we need to see what is like. I'll write the names here. Maybe if you're interested, you can search about this. If you want to study about residues, we need to know two things. One is singularities, and other is Lorentz series. So these things, explaining about this itself will take some time, some 10 minutes or so, or even more. But for the time being, I'll restrict myself to a simplified version of Cauchy's residual residue theorem. So there are different kinds of poles, right? We can have a simple pole, like something like there is no power with the pole. But I can also have something like f of z by z minus a whole square. This is also a pole. But this pole is having a multiplicity of 2. So in general, suppose z naught is a mth order pole of f of z. So what I mean is that I have f of z is something by z minus z naught raised to m. This is the meaning when I say that z equal to z naught is an mth order pole of the function f of z. Till now it's clear, right? I'm about to say the statement. So is the setting clear? Like, shall I continue? If there's something not clear, like please let me know. Because I skipped many things. Can I continue, right?
Yes, sir.
Okay. Thanks. So now again, once again, like the definition I'm giving here is a simplified definition. The residue is a bit more general thing, but for the time being, we will focus only on residues of these kind of poles, this z minus z raised to m. There are other kinds of residues which I have not seen in gate exam, but in complex analysis it is there. So yeah, now okay, we have a pole of order m. Now then, by the way, I did not tell what is residue, but let us suppose there is something known as residue. Now residue of the function f of z at the point z equal to z naught. So that thing we denote like this. Residue of the function f of z at z equal to z naught is defined by this formula here. 1 by m minus 1 factorial limit of z going to z naught d raised to m minus 1 by dm raised to m minus, I mean dz raised to m minus 1. Basically, this is the m minus 1 the derivative. M minus 1 derivative of what over here? Z minus z naught raised to m f of z. So this is a complicated formula, and yeah, when you see it for the first time, it could look very complex, but it's not that hard. Also, like at least for our purposes, it's not that hard. So, special case, suppose it is a simple pole. Now, residue for the first order pole. Suppose let's Z equal not be a first order pole, then m equal to 1. That's the idea. So if we substitute m equal to 1, the residue for the first order pole can be found at limit of z go to z naught, z minus z naught f of z. This is the residue of the simple pole. So these definitions, is it okay? Like if it is not clear right now, like maybe you can take a look at it again, but in a bit more, I mean, what to say, like that needs more relax or something like that. This looks a bit difficult, but this is the definition, and this is a simplified definition. The actual definition of residues is a bit more involved. So, but yeah, so the moral of the story is that whenever we have a simple pole, then the residue is defined like this: limit of z going to z naught, z minus z naught, f of z. Now, if you have multiple order, what we do is we will differentiate this part and put a power here. That's it. That's why you're getting like this. So what I'm explaining is that if I have m equal to 2, then I'll be first doing z minus z naught square fz, then I'll be doing differentiation, and then I'll be doing the 1 by m minus 1 factorial outside the limit. That's how we write the formula. But again, like if it is hard to recollect in the first go, it's okay. Like it's okay. So just to be sure that uh, the point is that we should be aware that there is something like this. That's the only thing. So the formula, once you apply, it's not that hard actually. So now what is the theorem actually? So far we discussed what is a residue. Now what is a residue theorem? Again, that's a simplified version here I am presenting. So let Z1 up to Zn be poles. of a function f of z inside a circle C. It need not be circle, but any simple closed smooth curve C. Now, suppose a function f of z is analytic everywhere within the circle except at the poles. So, except at these certain points, the function is analytic everywhere. Then, integration over C f of z dz is given by 2 pi j times sum of residues. This is the Cauchy's residue theorem. Now, a special case of this theorem, when we have a single pole with a single order, that is the Cauchy's integral formula that we use, what we are usually used to. But again, so this is the formula. This is what the conclusion is, that integration over C f of z dz is 2 pi j times sum of residues. This is the idea that we have here. So till now, is it okay? I mean, I'm sure that there will be doubts, but yeah. So the definition itself is quite complicated. But shall we see an example? I think that's better. I think. Can I continue?
Yes, sir.
Okay. So this is again not a very hard question. Like I don't want to take a hard example also. So let us see this. So what is this function? I is integration over C z square minus 1 by z square plus 1 dz. This I can write like integration over C z square minus 1 z minus I or j, what? Okay, I only z plus I dz. Up to here it's fine. No, we do the
Sir, e
usual
to the
step
power
only.
is left.
Sorry,
E
sorry,
to the
sorry. Yeah,
power
yeah,
left.
yeah, 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 yeah. Thanks. Yeah. So up to here it's like our usual thing only. Like we have a function, we split the denominator and do things like that, and then we want to write like z minus a or something like that. But now what happens here? If you see the region here, we have two poles. Both are symbol poles, but there are two poles at I and minus I. Even that is fine. We know how to handle that. There is a pole at minus I, there is a pole at I. Up to here, it's same as what we are doing till now. But now the catch is that the, the circle or the whatever the shape that we need to integrate, that is mod set equal to 3. So that circle is something like this. It is not a small circle, it's a big circle. And that big circle contains both these poles, not just a single pole. If it is a single pole, we can use the Cauchy's integral formula and we can get the answer, not a problem. But here, we have two poles in this circle. So whatever we were doing here, this thing won't work because there are two poles. So to answer such question, we need to use Cauchy's residue formula. So sorry, Cauchy's residue theorem. So what the theorem says, the theorem needs the function to be analytic on all points except at the poles. So consider f of z to be my entire function, like z square minus 1 e raised to z by z minus I z plus I. Not that I'm not writing f of z by something, but I'm calling the entire thing as f of z. Now what we can note is that not that f of z is analytic inside the circle C everywhere except at z equal to I and z equal to minus I. Because for any other value, we have this much part is a rational function and this is exponential. So exponential functions are also analytic. So in this entire function, except at the points where the denominator is becoming 0 or the function is becoming infinity, this f of z is analytic. The statement is clear, right? It's different from what we did before. What I'm telling now is that this function f of z is analytic everywhere inside the circle except at these 2 points. Correct, no? Is that okay? Shall I continue?
Yes, sir.
Yes, sir.
Okay. Okay, thanks. So, what it means is that we can now consider the residue formula. What does that mean? Integration over f of z dz is 2 pi I times sum of residues. This is the residue theorem. So, what are the residues? We will be having two residues. One at z equal to I, other z equal to minus I. So, the residue, So residue of f of z at z equal to I. This is how do we define that? If you recollect the definition before, this is how we define the residue. But in this case, we have m equal to 1. It's a first order pole. So we don't have this complicated business. We have this simple expression. Now this simple expression, at least this we have to remember. But again, it's good to remember this also. But yeah, so this one we can directly use. What it means is that this residue at z equal to I is limit of z going to I, z minus I, f of z. I am just writing the formula as such, no difference. Z goes to I, z minus I. I have my entire function here. Z square minus 1 e raised to z by z minus I, z plus I. Now this z minus I get cancelled out. I get limit of z go into I, e raised to z, z square minus 1 by z plus 1. So now I can, nothing is going to infinity here or 0 here. So, I mean, denominator is not 0. So, I can substitute I here. What it is, e raised to I, I square is minus 1. So, minus 1 by, uh, this is I, not 1, 2I. So, this is like minus 2 by 2I e raised to I, or minus 1 by I e raised to I, or I can write I e raised to I. Why did I write that? Because 1 by I is same as minus I. These are same. So, to conclude, residue of the function f of z at z equal to I is I e raised to I. Is that okay? Residue is a number basically. So, up to here is it okay?
Yes, sir.
Okay, thanks. Now, what do we need? We need the other residue. So, what do we have? Residue of the function f of z at z equal to minus I. What is it? This is limit of z going to minus I, z plus I, f of z. This is limit of z going to minus I, z plus I, f of z is again like z square minus 1 e raised to z by z plus I, z minus I. This is same as limit of z going to minus I, z square minus 1 e raised to z by z minus I. Now I can substitute this here. It's again minus 2 e raised to minus I by minus 2I. This is like minus I e raised to minus I. Is that okay?
Yes, sir.
Okay, right? Okay, thanks. So, therefore, we now know what are the residues of both these functions. We have found out the residue of the first one is this thing, and residue of the second one is this thing. Therefore, by Cauchy's residue theorem, we have integration over C f of z dz is 2 pi I times sum of residues. So that is I e raised to I minus I e raised to minus I. Correct, no? Up to here, any doubts? Continue, right?
Yes, sir.
Okay. So what does it mean? This is 2 pi I times e raised to I minus e raised to minus I, or minus 2 pi I and I becomes I square minus 1 e raised to I minus e raised to minus I. Now note that sin x can be written like e raised to x minus e raised to minus, sorry, I can write sin x as e raised to ix minus e raised to minus ix by 2. This is correct, no? This is how we can write sin x. So what it means is that I
2j
have, yeah,
upon
of course, yeah.
2j.
Sorry. Yeah. That's it. Yeah, thanks. So that means I can write this thing as minus 2 pi times 2I times sine of 1, right? It's correct, no? 1 means like just x equal to 1, that's it. This is like e raised to I minus e raised to minus I by 2I. Correct, no?
Yes, sir.
Okay. So what it means? This is minus 4 pi I sine of 1. That is the value of this integral. Let me see if that's in the option. Should be there. Yeah, it's D, option D. So option D is the correct answer. Is that okay? It's a bit complicated, but it's not very hard also. Like if you think about the formula, it's not very hard. I think maybe we can do one more question. Uh, what if the pole is on the contour, right? Okay, that part I need to think actually. So from the gate point of view, I have not seen a question with that, with the pole on the contour. But from a complex analysis point of view, I am not very sure. I need to think about that. So things get sticky when it's exactly on the pole and things like that. So yeah, I think most likely we will not be able to do the integration, I guess, because at some point that function value on the integral path becomes infinity. So that's kind of, it's either not defined or something of that sort. Is that okay?
Yes, sir.
Okay. Okay. Thanks. So maybe we can do one more question. I think we have time for one more question. So shall I do this question? Okay, right? Any doubts in the previous questions? That I can do this, right?
Yes.
Okay, thanks. So this question is from a different topic. It's actually on Laplace transforms. So the question is like this: let x1t be e raised to minus t ut, and x2t be ut minus u of t minus 2, where u is our step function. If yt denote the convolution of x1t and x2t, then what is limit of t going to infinity y of t? So it's a kind of, it involves everything. There's time domain, there is frequency domain, there are convolution, there are two signals, things like that. So basically, we are given with two signals x1 and x2. We need to find the value of limit of t going to infinity y of t. Basically, the final value of this function y of t. So what do we need? So question is clear, right? Okay, no?
Yes, sir.
Okay, thanks. So what do we have? We have limit of t going to infinity y of t. This is same as limit of t going to infinity x1t convolution x2t, because that is the given in the question. Now, by final value theorem, we have limit of t going to infinity y of t is same as limit of s going to 0 s times y of s, where y of s is the Laplace transform of the function y of t. This is the final value theorem. Okay, no? If there is something not clear, please let me know. Now, what is y of s? Y of s is the Laplace transform of x1t convolution x2t. Now, this will be the product of the Laplace transform x1x times x2x. Because Laplace transform, if you do convolution in time domain, Laplace domain, that becomes the multiplication. So basically, what we want to find limit of s going to 0 s times x1s times x2s. This is the this is the result. By the way, this assumes that we can actually compute this limit. I mean, if the limit doesn't exist or things like that, then this final value theorem is not valid. But let us suppose that we can evaluate this. Let's see how to do that. So x1t is e raised to, what is it, minus t, yeah, e raised to minus t ut. Now if x of t is e raised to minus at ut, then Laplace transform is given by 1 by x plus a. This is a standard result that we have discussed before, and that's kind of quite standard. Now if using this formula, x1t will give to 1 by s plus 1, correct, no? Other thing is, suppose x1t gives to, let's say, x of t. So x of t gives to x of s, then x of t minus t naught will be giving x of s e raised to minus st naught. This is again coming from the property of Laplace transforms. Now we have, suppose u of t is my function. U of t will give 1 by s, basically e raised to 0 t u t. That is u of t. So what is u of t minus 2? Let's say 1 by s times e raised to minus 2s. Up to here it's clear, no? No issues, right? Can continue, right?
Yes, sir.
Okay, okay, thanks. So what do we have? The second signal y of x to t is u of t minus u of t minus 2. So I have x to t to be u of t minus u of t minus 2. Therefore, x to s will be 1 by s minus 1 by s e raised to minus 2s. So putting it all together, what is y of s? Y of s is x1s times x2s. This is 1 by s plus 1 times 1 by s minus 1 by s e raised to minus 2s. So I can write like 1 by s into s plus 1, 1 minus e raised to minus 2s. Okay. Now what I want to find, final value, limit of t going to infinity y of t. This is same as limit of s going to 0 s times y of s. This is limit of s going to 0 s times 1 by s into s plus 1, 1 minus e raised to minus 2s. S and s cancelled out. Limit of s going to 0, 1 minus e raised to minus 2s by s plus 1. And if you substitute, it is of the form 1 minus e raised to 0 by 0 plus 1, which is 0. Denominator is 1 and numerator is 1 minus 1. So the final value is 0. But okay? Any doubts? Shall we continue?
Yes, sir.
Yeah, I think we can do one more question. We have time for one simple question. Okay. So this, I don't know which year it was, but yeah, recent question. So we are given with three vectors: minus one, sorry, 1 minus 1 2, 7 3 x, and 2 3 1. So I have three vectors: 1 minus 1 2, 7 3 x, and not necessary. Okay, good. Maybe this one.
No, sir.
Okay, then we can do this. So, by the way, if we still have time and if somebody is having doubt in this question, we can do this also at the end if we have time. Let me, it's easy only. I mean. So, this is the thing. So, to solve this question, find determinant of 1 minus 1, 2, 7, 3, x, 2, 3, 1. Set determinant equal to 0, we'll get the answer. That's it. Okay. Now, coming back to this question. So, consider the matrix A, which is like this k to k, k square minus k, k square, and the vector x. The number of distinct real values of k for which the system has infinitely many solutions. So this question is slightly different. So to solve this question, let us see when will a system of equation has infinitely many solutions. Now consider ax equal to b. B can be 0, it can be nothing. Now the system has infinitely many solutions if rank of a is, by the way, let us, this is m cross n, this is n cross 1, this is m cross 1. Rank of a is same as rank of a augmented b, which should be less than n. If this condition is satisfied, then we say that the given system of equation has infinitely many solution. This is the standard result. It's okay, right? Basically this part says that there is a solution or system is consistent, and this says that there are infinitely many solutions. This is okay, right? Okay, continue. No?
Yes.
Okay. So in our case, what is this? M equal to 2, n equal to 2. So I want rank of A to be same as rank of A augmented B to be less than 2. It can be 1. Or I mean 0 rank doesn't make sense, but it can be 2. It can be 1 basically. Now, if you see here, B is 0, 0. And A is given in the question K 2K, K square minus K square. Now, so this first part is anyway true. So, rank of uh, K 2K, K square minus K square is always same as the rank of augmented matrix because we are appending a 0, right? So when you add a 0, rank will not change. So basically what I want to say is that adding 0, 0 will not change rank. That's a factor matrix series. So okay, right? So basically this rank of A is always same as rank of A augmented B in our case. So we just need to find when is the rank less than 2. That's sufficient. What it means is that to get infinitely many solutions, rank of A should be less than 2. So, or in other words, A is singular. 2 cross 2 matrix having rank less than 2 means it's singular matrix. So, what it means? This means that determinant of A should be 0. Let us compute that first. What we have here? We have K. What is K 2K, K square minus K and K square. This determinant should be 0. So, K cube minus 2K into K square minus K is 0. We'll take a K outside. K square minus 2K square plus 2K. This is 0 or K equal to 0 or K square minus, okay, this is again 2K minus K square equal to 0. What it means? K equal to 0 or K into 2 minus K equal to 0, which means K equal to 0 or K equal to 0 or K equal to 2. Now the question is that how many distinct values are there for this K? How many distinct values of K are there? So question is like this. So the number of distinct real values of K for which the equation has infinitely many solutions. Now what we shown is that this system has infinitely many solution if K equal to 0, 0, 2. So how many of them are distinct? 2 distinct values. So the answer is 2. Is that okay? Any doubts?
Yes, sir.
Okay, thanks. So I think that's 8 o'clock already. So I think that's mostly what I planned for today. And yeah, I just want to say a big thanks to all of you. So I think most likely this will be our final session for this time. And I know some of you are in third year, so maybe we can meet again next year. And for others and everybody giving gate, do consider IASC as one of your options. So hope to see you guys directly here. So this is also a first time experience in my life. First time I'm doing something like this. So thank you very much. All the best for the GATE exam and do well in life. Thank you.
Thank you, sir.
Thank you very much. Thank you.
Sir.
Thank you. So any other doubts? If not, we can conclude the session.
So can we contact in future?
You can mail me actually. You can mail me like
Okay,
that. I can give my mail ID. Live sessions, I'm not sure about that. Okay. Live session probably in April or sometime it will start. Not very sure when is that. So this is my mail ID. Yeah. Okay, so it was a good experience for me as well. I hope that something is useful somewhere. So will live session continue next also? So next week, I don't think it is there, but after some time it will again start. So that I think it's good to. Even I don't know when it will start next, but if it is there, then most likely I'll be also there. I'm interested in that. So yeah, I think after a break, mostly after gate exam, it will start again. So right now, what we are told is that Jan 31st is the final class. So next Monday and next Tuesday class will be there, but next Wednesday is February 1. So most likely class won't be there. If class is there, I think maybe we can meet, but most likely class won't be there. That's what I feel. So yeah. So next time, if I think I suggest you to check the portal. I think they will update when the class will start again. So yeah. Okay.
Oh, okay, sir. Thank you, sir.
Okay then. Thank you. Thank you very much for attending. All the best for Gate. Thank you.
Thank you, sir.
Thank you. Okay then. I am concluding the meeting. Thank you.